welcome everyone, and thanks for coming to my talk. So in my talk, I'll try to cover a topic which might sound really disgusting to all of our cloud-native ears, namely stateful applications and various ways of dealing with them on Kubernetes. If that sounds too horrible for you, the doors are still open, so you can still leave. And incidentally, this won't be a talk about storage. I've been asked a few times during lunch. So if you're expecting a talk on storage, again, the doors are still open. So, but no one's leaving. That's cool. So let's embark on adventures in stateful applications on Kubernetes. And just to make things extra adventurous, I've also prepared some demos. So please bear with me and also help me pray to the demo gods one last time. Before we dive in, let me briefly introduce myself. My name is Mathis Kretz. I work for Bespinion. We're a company based in Bern, and we specialize in all things cloud native. We help customers in successfully building, maintaining, and operating their applications on the cloud, either on Kubernetes-based platforms or based on serverless technologies in public clouds. So next time you're in Bern, feel free to drop by our offices in the Old Town for a coffee or a beer. So when we think of cloud-native applications and applications deployed on Kubernetes, we like to think of stateless applications, right? Indeed, we've probably all read the 12-factor manifest, where the 6th of the 12 factors states that an application should be run as one or more stateless processes, right? And why do we prefer stateless applications? Well, that's pretty easy, because we want to be able to scale the application components out horizontally, and keeping state in memory generally gets in the way of that. In this example, you see a component running with 2 replicas with a load balancer in front of it. And now, if each of these replicas is holding state in its memory, that state can potentially start to diverge, as you see suggested by the colorful shapes. And that in turn will lead to inconsistent behavior as requests reach one or the other replica, right? So this is a situation we generally want to avoid when building cloud-native applications. So far, so good. So how do we usually avoid this situation? Well, by using some external service like a database or a caching solution, which is made for persistently storing state, right? So replicas don't keep their state in memory, but instead they read the state from the external service, process the request, potentially update and write back the state to the external service, and then return the response. And since all replicas are reading from and writing to the same state, the inconsistent behavior that we saw before doesn't happen anymore. Assuming, of course, that we can offload the heavy lifting of concurrent data access to our persistence technology that we're using. Now that's really cool, but there are situations where we cannot follow this pattern, and where we're dealing with applications that are somehow inherently stateful. So one such situation is one we all know very well. This is when statefulness arises from the fact that our application needs to manage persistent data in a reliable manner. So our application is itself a database, or is itself a caching solution. So what tool does Kubernetes offer us in this case? And I know that's a pretty easy question to ask at a KCD conference, right? So yes, of course, stateful sets. But unless you're in the business of building databases on Kubernetes, chances are that you've never really had to work in detail with stateful sets yourself. So let's remind ourselves of what stateful sets are, and in particular, what their key features are. So stateful sets, like deployments, are ways, or give you a way of running an application with several replicas, right? However, in contrast to deployments, stateful sets assign a a unique stable index to each replica of an application. On our slide here, we've chosen the example of Postgres containers in each pod, which together will form a Postgres cluster. So the index determines the order in which replicas are started. So the replica with index 0 is started first, then the replica with index 1, then the replica with index 2, and so on. So this strict ordering allows your application to run some kind of clustering protocol and to initiate that protocol in a controlled way. And furthermore, the index can actually be made, can be injected into the container, or the container can know the index that its replica has and can base its own logic on that index. Another feature of stateful sets, which make them different from deployments, is that stateful sets allow you to assign a persistent volume to each replica. So here we're following the example of Postgres with the data directory of each Postgres pod. Furthermore, Kubernetes will guarantee that if a replica happens to go down, the new replica coming up with the same index will be able to mount the same volume again. And this will ensure that each replica has a durable persistent storage at its disposal. And the last important feature of stateful sets is that each replica gets a stable DNS name, enabling each replica to be addressed individually. This is again in contrast to deployments, where Kubernetes basically treats each replica as an anonymous thing to be load balanced over, right? So the stable DNS name enables two important things. Firstly, it allows replicas to contact each other under a well-known name for running some kind of clustering protocol. And also, secondly, it allows external clients to access specific replicas when this is required. For example, when you're doing a leader election thing, then your client will want to connect to one specific replica for a certain purpose, right? So now that we've looked at the theory, let's have a look at stateful sets in action. And for this demo, I've prepared a stateful set that is meant to be instructive and not really meant to do anything useful. So we can just review the features that we just discussed. So as you can see, this stateful set is called, let me quickly get the cursor on the screen here. So this stateful set is called example, and it consists of a container called listener, and that listener container does a very simple thing. It basically just listens on port 1, 2, 3, 4, 5 and echoes whatever it receives on that port. And you can also see how an application can know the pod index or the replica index. This can be achieved by using a label which is assigned by stateful sets to each of the replicas. So stateful sets assign the pod index label to each replica, and the value of that label is the replica index. And obviously that label can then be written to an environment variable like so, and the environment variable in turn can be read by an application and used to implement whatever logic you might need to implement based on this index. As a further example, or to demonstrate further, I've also added an init container to our stateful set. It's called announcer. And what the init container does is it basically simulates like a clustering protocol. So when you start up, when a replica starts up, the init container will say hello to all replicas with index lower than itself, right? So from this we can see that there is a strict ordering of indices, because we can assume that all indices lower than ourselves are already existing. And we can also see how we can contact other replicas, namely here by their canonical DNS name in Kubernetes. So let's give that a spin. And of course, I just apply this whole bunch of YAML. And oh, sorry. Thank you. It helps if you apply and don't delete first. So as you can see, the replicas are now coming up. And if I tail the logs of the first replica, you can see that it's indeed being contacted by the other replicas as they come up in turn. So that works like we've expected. You saw the ordering of the replicas arriving and the communication there. As a last thing, I can also simulate a replica going down. So if I quickly were to delete the pod with index 3, you'll see that the exact same pod with the exact same index is immediately reinitialized by Kubernetes and replaced. So that's also very specific functionality of stateful sets. Right, so now that we've reminded ourselves of how stateful sets work, let's think about what stateful sets don't solve for you when you're dealing with stateful applications. I mean, there's no magic, right? So firstly and most importantly, stateful sets don't magically make your application, your stateful application run correctly. I mean, how could they even do that? They don't know your application, right? What stateful sets do is they give you basic tools and guarantees so that you can implement whatever application-specific logic is needed in order for you to deal with your particular aspect of state. And secondly, and this will lead us to investigate other solutions to statefulness, stateful sets are very much geared towards statefulness deriving from persistent data. They're ideal for running databases and caches, which have several redundant replicas, and where scaling up and down is likely to involve heavy replication activity between the old replicas and the newly created replica. On the other hand, I would claim that stateful sets on their own are not ideal for the form of statefulness which we'll look at next, and I call that stateful computations. So what do I mean when I say stateful computations? So say you have some kind of sensor. In this case, we're using the example of a camera, which produces data frames over time, and you have an application which consumes the data frames and which computes some data model over time as these frames arrive. And say the person who designed this application and who wrote the application made one crucial assumption, namely that exactly one instance of the application is connected to exactly one camera. So the application is just keeping the data model in memory and updating it as new frames arrive. So in this situation, obviously, we have the challenge when it comes to horizontally scaling our application. So say a new camera is added or is hooked up to our system. Because the first replica of the application is already working on the first camera, we need to spin up a second replica and tell it to work on the second camera. Now, of course, you will say to me, this application should be changed, right? To become truly scalable. You should externalize the data model and have some way of enabling multiple replicas to work on multiple cameras. And I would obviously agree with you, but there might be practical limitations that we're dealing with. So we can, for example, the application code might be poorly understood, might be old. Maybe the data model is prohibitively large to make the round trip to some persistent service on every frame. maybe you just don't have enough time or budget to rewrite the application right now, right? So what other options do we have for running this application correctly? One thing that comes to mind is we could use an event streaming technology to control how the frames of the camera reach the application. So all such technology, be that AWS Kinesis, Azure Event Hubs, Google PubSub, or just plain Kafka, they have some notion of partitioning events. And partitions usually offer guarantees with respect to delivering events in the same order as they were produced. Plus, clients can subscribe to individual partitions, right? So we could ensure that each camera writes its frames into a separate partition, and also ensure that every partition is being consumed by exactly one client or one replica, and that might work. But maybe we don't have these services at our disposal. Plus, even if we did, we would potentially have to write a lot of additional automation for the use case where we're adding a new camera to our application. Another technology that could potentially help us is HashiCorp Consul. Consul has the notion of sessions and locks, which could be used to coordinate which replica is working on which camera, with sessions timing out if a replica's health check fails. However, Consul basically only offers us these primitives, and the actual coordination scheme would need to be implemented by the application itself. Furthermore, again, adding a new replica when the user adds a new camera would also need to be implemented in a custom way. And last but not least, again, you might not want to run an entire Consul cluster just to coordinate a couple of stateful replicas. So after reviewing the features of these technologies and each of their downsides, we came up with the idea of making Kubernetes itself support running stateful applications by adding, or running stateful computations by adding a few open source components on top of the standard functionality of Kubernetes. And because we're avid Star Wars fans, we of course had to give this new creation a Star Wars name. So who is good at coordinating things in the Star Wars universe? Well, one character that comes to mind is Admiral Akbar, the commander of the rebel fleet. So we called our new framework Akbar. And you can have a look at it on our GitHub. And of course, if you're interested, we can discuss it further, or you can contribute. So what's the idea behind Akbar? So Akbar is a little microservice that can be deployed just as a normal application on Kubernetes, and it offers an API for managing replicas of an application which runs stateful computations. So in the Akbar API, you start with what we call a context, which is what you see here, and a context is just one particular application which needs to be managed. And then within a context, we can create so-called partitions, and a partition is a data source which needs to be processed by a stateful computation. So sticking to our example, every individual camera would be a partition in Akbar. And a partition contains the configuration which is needed by a client to access that particular data source. So again, in our example, the partition will contain, say, the IP address of the camera in the network. So let's assume that we have an application which wants to process the data coming from each camera in the stateful way that we described before. So in this case, we can deploy our application as a deployment. Note, we don't even need to use a stateful set here, because Akbar will manage statefulness. And each replica of our application can then register itself in the Akbar API as a so-called worker. And once it is registered, it needs to send a heartbeat request to the API of Akbar to signal to Akbar that it's still alive and working as it should. And then Akbar distributes every live replica every live worker to a unique partition, hands the configuration to the worker, and the worker starts processing the data source. In addition, Akbar also calculates a metric called partition to worker ratio, which expresses whether there are too many idle workers or too many partitions which are not being worked on. And this metric is plugged into the Kubernetes metrics API as an external metric via a metrics adapter that we wrote for Akbar. So if a new camera, and this, the fact that we're exporting this metric also makes the metric accessible to a horizontal pod autoscaler, which we can define, which we can use to scale our application as needed. And the horizontal pod autoscaler will just ensure that the partition to worker ratio is always at the value 1. So what happens if a new camera is added by the user to the application? Well, in that case, the partition to worker ratio will temporarily go above 1 because there are too many partitions now. There is one partition that is not being worked on. This will be picked up via the metrics API by the horizontal pod autoscaler, which will in turn spin up a new replica. It will scale out the deployment by 1. The replica will register as a worker. Akbar will assign it to the free partition, and our state is, we're again balanced, so we have all our data sources being worked on. So that's all very well, looks very nice on slides, but of course, this needs a demo. So let's head over to our terminal again. So I have an instance of Akbar running on my kind cluster here on my machine. And the first thing we can look at is the context. So this instance of Akbar has 2 contexts that it manages, demo context 1 and demo context 2. We're going to be interested in demo context 1. And as you can see here, the partition to worker ratio of demo context 1 is 1, so we're currently in a balanced state. There is exactly as many workers as there are replicas. Incidentally, we can also look at the same metric in the metrics API of Kubernetes by contacting the metric API directly. And you can see here the same metric in Kubernetes format, so value 1, and we can select by context using a label selector. Now let's have a look at how many data sources we have configured, and that is again a request to Akbar's API, namely the partitions endpoint. And you can see we have 3 data sources currently configured. And you can see each data source has this configuration block here, which has the fictitious configuration information, the IP address, the port, and say a device name, right? Let's have a quick look at the workers in our system. So we have 3 workers happily running. And we can also very quickly look at the horizontal pod autoscaler that is behind our example client. you can see it's acting on our deployment, and it's striving to keep the partition to worker ratio metric at value 1, right? Right, so what if we were to add a new camera to our application? Well, we would do this by posting a new partition to the API. And you can see here I'm posting the configuration of this new partition. And when I do that, you'll see the partition to worker ratio go above 1 for a short time. Then you'll see the horizontal pod autoscaler acting, scaling out, and we'll hopefully see everything going back into a balanced state. So as you can see, I've added the new partition. We're seeing the horizontal pod autoscaler becoming active, actually overreacting because it now created 2 replicas, which makes the partition to worker ratio go below 1 for a short while. That will be compensated in a few seconds again as the autoscaler removes that superfluous replica. And we end up with 4 partitions, which now are all being worked on as we expect. Right, so that actually brings me to the end of my talk, my session. Before we open for a few questions, there's one question I'd like to ask you, and namely, is it just us, or do you also think that something like Akbar might be useful to have as a tool on Kubernetes? So the question is simply, could Akbar be useful? And if you want to help us, you can quickly answer our Menti poll, and then we can open for question at the same time, I guess. Yes. Let's quickly. Yes. Yes.
Yes, about the partition configuration, you posted it to the Akbar service, and where does that configuration get stored? Does it store it locally, so it needs EBC, or can this be adopted in like a operator grade, so you have like a CRD of the context you can post then, or?
It's actually would be a very nice idea. Right now, we just have a little Redis that we store the configuration or the data of Akbar itself in. But it's actually a nice idea to store that in etcd of Kubernetes, probably. That would be even cleaner, because then you don't need to like maintain a Redis.
Yes, but also can manage it by DevOps or
yeah.
part of CDs.
Yes.
So in this example, you had 3 partitions, right? What happens if the second partition goes away or is now empty, the second camera, but the horizontal pod autoscaler removes the 3rd pod, because maybe from his point of view, that's the logical thing to do, right? Because it's just the 3rd replica of this deployment. Yes. And then partitions and pods wouldn't match. You would lose the state, right, of the 3rd partition, and you still had the pod which formerly was working on the 2nd partition up and running.
Yes, that is actually a really good question, and I was hoping that no one would ask it, because it's actually a weak point right now of the whole horizontal pod autoscaler approach, that you can't control which replica is removed if a scale down happens. Yeah, we might need to put more thought into that aspect if Akbar actually becomes a thing. Yeah, yes, yeah. I agree.
Yeah, I guess you would probably have to write your own controller that manages multiple deployments instead of one deployment with replicas, because I've seen this pattern used, for example, in CNPGIO, where they don't use stateful sets or a deployment with replicas, but they create 3 different deployments with one replica, and they manually control it with their own controller so that they really know exactly what's going on.
Yes.
Yeah.
good point. Thanks.
I had the same question, so. Perfect. Any more questions right there?
Yeah, do you have some real-world example for this approach with ECBA? Because now with the example you've given, I'm a little bit confused because you are just externalizing the configuration of an application. So the application reads the configuration through ECBA, through the API, and you manually configure ECBA from the outside through API calls. Why don't you just provision a new pod with an environment variable with that configuration?
Yes, that could be done. In this case, we had the case that this is an application where there was an application where sensors could be added and removed essentially by the user, by the customer, and having to act on the Kubernetes control plane every time someone is adding, in a sense, a new sensor. That would have not been an option in this case. That's why we came up with this solution, so that basically the application could easily integrate with something that is not Kubernetes itself. Yeah.
Perfect, thanks.
Okay.
And also, also this could also be used on something which is not Kubernetes even, right? Yeah. So.
Unfortunately, we have to wrap this up. I'm sure Tis is open to questions afterwards. Thank you very much, Tis, and another round of applause. Thank you.